Hi, so this presentation is for the ICITST conference, and the name of our presentation is for computing for IoT devices in motion. So my name is Denny, and I work along with Amit Prabhakar and Professor Aspen Olmsted. So let's just quickly start on what is cloud computing. As you all know, cloud computing is the thing of the future, and it's what's booming right now. So you essentially can deliver anything to the cloud, and then you can, like, your software, your storage, your database, and you pretty much can host anything to the internet now. So any dumb device can connect to the internet with IoT. So this is what I'm going to be covering today. So how IoT and cloud computing has issues and how it can be solved. So of course, there is a lot of cost saving with cloud computing, and there is a lot of speed up. The scaling factor of the cloud computing, you have a lot of devices connecting to the cloud, and you have, of course, productivity and connectivity that comes with the cloud. So just to get you started, I just wanted to give an intro on cloud computing. So, but there are some issues with cloud computing. So, since it is on a network, so you can have congestion, can have latency between your request and response, you can have poor quality of service, but these are fine for ordinary applications. But what happens when you have critical applications such as your health status monitor, such as your connected car? So something has to be done in that case. And essentially why IoT devices can have problems with only the cloud. So these IoT devices need the geo distribution, the low latency, the mobility support, where if you go from cover a distance, it has to you should get good mobility range over there. And then how do you solve all these? So we need to use the cloud anyway. So the solution that has been of prominence lately is fog computing. So that is a new platform that works on top of cloud, which your IoT devices can talk to. So it's essentially fog computing is a network in between your cloud data center and your device. So it essentially is fog. It's called fog because it brings the cloud back to the ground, or you can think of it as it brings the cloud near to your device. So essentially, in that with that, you get low latency because it's nearer. You get reduced bandwidth. You don't have to go all the way to the cloud to get your data processed. You get more privacy, but still have privacy issues, but still you get more privacy because it's not going up to the cloud. And then context awareness, because your this fog that is near to you can actually uh, listen to your data more personalized. So you get more context, you get more data analysis from the devices. So so also not fair. So fog computing has some issues. So these are just some of the issues, and I'm going to be talking about the mobility issues. Of course, it has security aspects and structural issues, because since this fog is actually a network of routers and switches and computing devices near to your IoT device, it has to have this. We have to put up the structural. Sorry, we need to have the structure around you. So I'm going to be talking about mobility. Sorry. Okay. So what is mobility? So when you travel from one place to another, you in a fog network, you have to pass through different fog nodes. The fog nodes are the things that service your request. The nodes that service your request, you can think of them as a small data cloud data center that process your personalized requests. So but these have a small range, and you need to switch between fog clouds, fog nodes when you are on the move. So but this can be a problem if you have a sensitive application such as connected car. So if you have a little latency between this handoff period, so in that period there is no data, so anything can happen in that time. So it could be seconds of delay, it could be milliseconds of delay, you cannot say. So we need some way to reduce that handoff. So this project is essentially reducing that latency and giving a hypothesis on how to do that. Also, you can see in the case of virtual reality, you need a very good response rate. And if you have a delay, that's going to be unacceptable for your projection to be true with your what you perceive. And in the case of healthcare apps, yeah, that should always be monitoring you, especially if you are in a critical case, or if you're on the way to the hospital, or in the case of an emergency, it has to have that 100% connectivity always. So let's see how we can solve this problem of mobility. So I'm going to start with what the problem is, like what is how a fog computing problem arises. So there are three things that we need to think about in fog computing. One is the when and the where and the how. So with regard to when we need to migrate to another node, we can say that we can continuously migrate, always give it the best possible node, but that is not very convenient because too much frequency can actually cause very much bandwidth, can consume lots of bandwidth, and that means a lot of downtime. And if you want to know like where to migrate, it would be ideal to like use the fog component and connect the component to the fog node, which is the very closest. But it might always be true because that one might be a little congested, or it might not be up all the time. So that is a problem with where and how. So what techniques do we use to migrate to another one? So that's what we are going to be seeing in the next slide. So then proposed algorithm works like this. So usually the fog networks can or can't or won't or don't need to keep track of the context aware information. What is the context aware information? It's information that is understanding your device. If the fog nodes understands that your device is standing there, or it is using its battery status 50%, it's a context aware information. So this algorithm uses those type of information to give a better handoff time. And how it works is the node tracks the location currently of the device and keeps track of it continuously. And if it sees that it's drifting away from that, and we can see that it's going to migrate soon to another node. And also, if we can also look at the state of the network link between the device and the node. If that is deteriorated, if that is on the decline, if the quality of the network link is on the decline, it's better to give that link to another node which can service it better. So we parallelly keep in track these two parameters. And then when we reach a threshold, we check for we check for the migration condition that we reach the threshold. So it's better to hand it off to someone. But that is where the problem arises, because usually the handoff takes a lot of time. So what I'm proposing is use predictive steps like this is gonna migrate soon. So why don't I give some data to the node? Why don't I populate the node before I give him off? So if I do that predictive step, I can essentially save a lot of time in setting up where the new node sets up with the new device. So I just give some information to the new node that this was the data, and I've pre-fed some data for him to process. So that can be done, and the new node instantiation can essentially be done by the old node itself. So it so essentially we're saving a lot of time. So how do we test this? So testing takes considerable resources, so I was not able to test this. But I was with the resources that I have, with the algorithms that I researched, I've decided on using aggressive prefetching. So get a lot of data to compute ahead of time and give it, if possible, to the new node. Otherwise, you just skip to the new node instantiation and then direct that new node, the device to the new node. The new node selection will also be part of the device. So if the device has if the new node is congested, so we can also select another node that is nearer, but that not too congested. So these are the steps that I propose. And yes, that's it. Thank you.